The Neuralink system relies on the N1 sensor, which monitors 1,024 independent electrical channels. This high-density array captures the minute voltage fluctuations generated by neurons in the motor cortex during planned movement. A specialized surgical robot inserts threads thinner than human hair into specific cortical layers. The robot uses advanced computer vision to avoid surface vasculature, ensuring minimal tissue trauma and preserving the blood-brain barrier integrity. Each thread is constructed from polyamide, a flexible, biocompatible polymer. This flexibility allows the electrodes to move with the natural pulsations of the brain, reducing the risk of chronic inflammation and glial scarring. Electrodes detect extracellular action potentials, which are rapid changes in electrical potential across a neuron membrane. These spikes represent the fundamental unit of information transfer within the human central nervous system.
The N1 chip amplifies and filters these weak analog signals before converting them into digital data. This local processing is critical to minimize noise and reduce the data bandwidth required for wireless transmission. Data is transmitted wirelessly through the skin via a low-power radio frequency protocol. This allows the user to interact with external devices without the need for physical connectors or transcutaneous wires. Algorithms on the receiving device perform spike sorting to distinguish activity from individual neurons. By analyzing the unique shape of each waveform, the system can isolate signals from thousands of separate sources. Neural activity is often represented as a point in a high-dimensional space. Researchers have found that these points typically lie on lower-dimensional structures called manifolds, which capture the underlying intent of the user.
The decoder identifies specific patterns of firing rates that correspond to desired actions. These intent vectors are then mapped to digital commands, such as moving a cursor or selecting a specific character. One effective method involves the user imagining the act of handwriting. The system decodes the intended pen strokes in real time, translating mental effort into high-speed text entry for programming tasks. Recurrent neural networks are used to predict the most likely intended characters based on the history of neural activity. These models excel at handling the temporal sequences inherent in language and code. Translating thought to code requires more than simple typing. The system can be trained to map complex neural states directly to abstract syntax tree nodes, allowing the user to generate entire logic blocks at once.
The implant is powered by a small internal battery charged inductively through the skin. This eliminates the need for internal chemical energy sources that would require frequent surgical replacement. To protect delicate brain tissue, the N1 sensor carefully manages its power output. Sophisticated sensors ensure that the temperature of the surrounding cortex never increases by more than 2 degrees Celsius. Low latency is essential for a fluid user experience. The entire pipeline from neural firing to screen update must occur in under 100 milliseconds to maintain the perception of direct control. Advanced versions of the system provide sensory feedback by stimulating specific neurons. This allows the user to feel the position of a virtual cursor or receive haptic confirmation of successful code execution.
Calibration involves the user performing known tasks while the system records their neural responses. This data trains the machine learning models to accurately interpret the unique neural signatures of that specific individual. The human brain is remarkably plastic and can learn to optimize its own signals to better suit the decoder. Over time, users often find that the mental effort required to generate code significantly decreases. Chronic gliosis, or the formation of scar tissue, can insulate electrodes from neurons. Neuralink addresses this by using small, flexible threads that minimize the chronic mechanical irritation that triggers the immune response. Kalman filters are frequently used to smooth out the noisy output from the neural decoder. These mathematical models provide a best estimate of the intended movement by combining current data with past states.
Beyond simple text input, the system can identify high-level cognitive states. This enables the user to trigger complex refactoring tools or debugging sequences through abstract mental shortcuts rather than manual typing. When a human makes a mistake, the brain generates an error-related potential. The system can detect this signal to automatically undo the last action or highlight a bug in the code before the user is even consciously aware of it. Security is paramount in brain-machine interfaces. All data leaving the implant is encrypted to prevent unauthorized access to the user's neural patterns, ensuring that their thoughts remain private and secure.
Future iterations aim to increase the number of electrodes to tens of thousands. Higher bandwidth will enable more nuanced control, allowing for simultaneous manipulation of multiple variables in complex software architectures. Modern integrated development environments are being adapted for neural input. These systems prioritize autocomplete and predictive logic to maximize the efficiency of the relatively low bitrate provided by current neural interfaces. Maintaining a high signal-to-noise ratio is a constant challenge. Environmental electrical noise and physiological changes within the brain must be filtered out to maintain precise control over the coding environment. Individual neurons are often noisy, but the collective activity of a population provides a robust signal. The decoder leverages this population coding to ensure stability even if some electrodes lose signal over time. The neural translation layer is designed to be language agnostic. Whether the user is writing Python, Java, or C++, the underlying motor intent is the same, allowing for versatile cross-platform development.
Recursive least squares algorithms allow the decoder to adapt to signal changes in real time. If an electrode shifts slightly, the system automatically recalculates the optimal weights to maintain performance without requiring a full recalibration. By applying microstimulation to the somatosensory cortex, the system can simulate the sensation of touch. This feedback is used to create a more immersive coding experience where the user feels connected to their digital environment. The brain's visual processing speed is utilized to confirm code changes. Rapid visual updates are synced with neural commands to create a tight loop that allows for fast iteration and debugging. Decoding does not happen in discrete steps, but rather as an asynchronous stream. This allows the system to react instantly to sudden changes in user intent, which is vital for high-stakes real-time programming.
Some users are exploring direct mapping to low-level assembly instructions. This bypasses high-level abstractions and allows for extremely precise control over hardware registers through direct neural modulation. Writing code with a brain interface can be mentally taxing. The software includes load management tools that adjust the sensitivity and complexity of the interface based on the user's current fatigue levels. State-of-the-art decoders now utilize transformer architectures to understand long-range dependencies in neural activity. This allows the system to better predict intent during complex multi-step coding tasks. The efficiency of the interface is measured in bits per second. Ongoing research focuses on maximizing this bit rate to eventually surpass the speed of traditional physical typing and mouse interaction.
The surface of each electrode is coated with advanced materials to improve electrochemical stability. These coatings facilitate efficient ion-electron transfer while resisting the corrosive environment of the brain. With thousands of channels, raw data volume is immense. On-chip hardware performs lossy compression, specifically tuned to preserve the information contained within the neural spikes while discarding irrelevant background noise. Debugging becomes more intuitive as the system can flag inconsistencies between intended logic and actual code execution. This allows developers to catch logic errors during the very moment of creation. In addition to single neuron spikes, the system analyzes multi-unit activity. This combined signal represents the average firing of a cluster of neurons, providing a reliable backup when individual spikes are hard to isolate.
Neural signals are mapped into a codebook of discrete vectors using vector quantization. This simplifies the complexity of the brain signals into a set of standard digital tokens that machines can easily interpret. The most effective systems treat the user and the AI decoder as a single integrated unit. Continuous feedback and adaptation ensure that both the machine and the brain are learning to communicate more effectively. We are approaching a new era where bandwidth will no longer be the bottleneck. Increasing electrode counts and improved decoding algorithms will eventually allow for the seamless translation of complex abstract concepts directly into software. All neural interfaces must incorporate privacy by design. This includes local processing of sensitive data and clear user control over what information is shared with external applications and cloud services. The translation of thought to code is no longer theoretical. By bridging the gap between biological neurons and digital logic, we are fundamentally changing how humans create and interact with the digital world.